domain and a range part. The x-intercepts and those things all and or about. Sure. I would prefer that you go straight to it because you won't be getting a calculator. And that's the practice that I wanted you guys to have. Because when we get to the overly complicated stuff, you understand how you start with generic value, how you can relate it. It just makes everything easier. That's why I picked these problems, because they're quick. And even though you get some crummy looking fractions on some of those, shouldn't have been so bad. Was there anyone in particular you guys wanted to look at? Because I know that the 12th hour, it was just 2 people we had to throw out. And did you guys do okay coming back to this stuff? It was pretty decent. Because I know first hour with so many people that were out doing tests and stuff like that, that's why they kind of. This is called dramatic pause. Hi, Devin. All right, so let's do this then. Let's just look at, hold on, because I'm going to collect this one with the 8.3 tomorrow. We'll just talk about 8.3 real quick. 8.3 is just more graphic. Did you notice that the only difference between growth and decay were your D values? Growths went up, or they dived away. Decay went the other direction. Pretty easy to look at. So when we get into, let me open up the next one. I'm not saving this one. Yeah, I didn't save it. All right, give me 1 second. The number E, it's fun, which means E is not 11. No, this is important to be watched. Oh, hold on for it. Give me 1 second. I don't want to. Generally speaking, before I've normally done this one after I've done a few of the word problems with compounding interest problems. But knowing that I was gone yesterday and first I didn't have a good chance to get through some graphing stuff, this is a very, very easy section to talk about via the graphs. So I thought I would do this one today because I knew that it only takes about 15 minutes or so to talk about. That way I could get first hour caught back up because, like I said, you guys did get the advantage of seeing a full-on how do you do all the exponential growth decay and things like that. So it worked out cleanly. It's a Hardwig. Hi, Jimmy. Where's my volume? I had that kid in class. I don't know why the volume keeps dying. Anyway, so one of the things that we talk about in 8.1 and 8.2, which we're going to do tomorrow, we talk a bunch about compounding interest. And one of the formulas we look at has this nastiness in it. And what this means, and I'm going to don't write any of this out yet. What this is getting to is what we're going to do tomorrow. It's for when you're compounding interest. So you can have interest in a bank. It says it'll compound annually, which means it compounds once a year. Semi-annually, compounds twice a year. Quarterly, 4 times a year. Monthly, daily, whatever. What happens here is, as this value of n gets larger, as it approaches positive infinity. The more times you compound your interest, this whole formula equivalencies out to this value of that 2 point something or other. That's what that kind of stands for. It's not that you have to ever know how to derive any of this, but what happens is whether or not you're using this formula for E versus a compounding continuous or compounding interest problem, it will tell you it's compounding continuously E. That means it's using E versus it's compounding quarterly or something like that. Trust me, it's super, super easy. What I wanted to do is just talk about the graphs of this first. Right. So we get stuff like this. We're going to look at the same basic principle where we have y equals a times b. Actually, I think they use r. Make sure I use the right one. Oh, let's do this first. They also do this. You can treat E just like you would pi. You were saying, hey, E is smaller than pi. Is it not as important? Well, no, it's still just some value. It's just some representation of a number. Pi is representation of the ratio from the circumference to the diameter. Circumference to the diameter thing? I don't know what it is. And then if you start getting into you really think about what it means with like exponent rules. E cubed times e to the fourth. Well, wouldn't you treat that the same way as you would e to x to the third times x to the fourth? So take a guess what you think e to the third times e to the fourth would be. Well, if you had more fingers, you would be able to get to 7. So you got to be careful in your shop class. Otherwise, I'm going to call you Stumpy. Okay, stick. What do you think happens when you have 10e to the third subtract or divided by 5e squared? Or not 2e? Yes, I just tried to go Shakespeare on that. Did you just get that? Sorry. Wow. So lastly, to be honest with you, this last one is one. Jeez. This last style is the one that usually messes people up, because if you look at what you have here, you've got all stuff being raised to the second power, and you have to treat it like you would any other variable. So you have 3e to the negative 4x. Well, that means we're going to distribute out our power stuff. If you go long form here, you know what? This is going to be 3 squared times e to the negative 4x squared. You okay with that? Now, 3 squared. 9, very good. All right, woo. Now, e to the negative 4x squared. No, it's e to the negative 4x on a squared, not shoot. So, hey, I missed out on a day. It was a pretty bad day. So, I'm trying to make up for it. Isn't that power to power? What do you do? That's fine. And then should I have any negative exponents? There you go. What most people do is they'll try to square the x. The x is part of the exponent, so power to power. The x is part of the exponent. Which gets me to be able to do that. Let me do that. What the graphs look like. Again, don't write any of this out. What happens here is that you can get growth and decay for E graphs. The only thing that changes is what the value of R This value of r that gets thrown into the exponent tells you if it's growth or if it's decay. A lot of times I've seen on on like standardized tests and stuff, is this growth or decay? A growth, B decay. Which is it? So it's just being able to identify what the value of r is. This value of r is going to be some sort of a rate. This rate can be fractional, decimal. It can be either greater than 0 or less than 0. If it's greater than 0, it is growth. If it's less than 0, it is decay. Pretty easy to decipher which one is which. So you'll see that this is very similarly written for growth and decay. Y equals A times P to the Rx. Where you have your B value now is this numerical value of E, and then it's just raised to some rate times X. Does that mean we'll have an H and a K? Yeah. Yes, sir. B is, as long as B is just not equal to E. Yeah, that's really all there is. So the value of B, when we were talking about growth and decay earlier, is that when we had Y equals A times B to the X minus H plus K, it was growth when B was, when B was greater than 1. It was decay when it was between 1 and 0. Whereas now it's the rate value. If the rate is negative, it makes the fractional amount, which gives you 1 over E, which becomes between 0 and 1. Does that make sense? Yes, sir. It was E over 8. That means A is 1/8. Does that make sense? Correct. The 1/8 then would just be like some scalar, like it was with the -1 times the quantity 2/3 to the x. That -1, it rotated over the axis as opposed to being straight up. It rotated down. That's what this stuff does. It's pretty simple. The only yes, sir. What's weird is that E is a kind of a crappy number to figure out any numbers in your head. But what is anything to the 0 power? 1. So what happens here a lot of times, we're just going to wind up using the value of x equaling 0 to decipher where your y-intercept is. And then we just draw a quick graph via, is it a growth or is it a decay curve? And that's really all you can do with these things. Shifting it, if you know where your intercept is, you just move it left and right, up and down. You'll notice these graphs here, we still wind up, they follow the same rules of the other stuff we have, excuse me, how the growth goes up and to the right, or it's going to dive down to the right if the A value is positive or negative. It all kind of flows the same way. So when we get to one like this, if I do y equals 2 times e to the 0.75x, or 3/4 x, however you want to write it, it's really, really difficult for me to create what we would normally do is -2, -1, 0, 1, and 2. It's really hard to figure out, well, e to the negative 3/4 would be negative. I can't do this in my head. 6 over 3/2. I can't do e to the negative 3/2. I don't know what that number is. I don't care what that number is. I'm not going to multiply some decimals. So what I do here is I'm just going to be using that. So a lot of times when we graph e ones, we just look at this. At 0, when x is equal to 0, what's e to the 0? 1. So when x is 0, what's y? 2. Is this one then, is it mirroring as a growth or a decay problem? decay because my rate is less than 0. I'm sorry, did I say that? I did the same thing earlier. It's growth, I'm sorry. Because this is positive. I'm still thinking B value. I'm sorry, I apologize. So this is, since your R value is greater than 0, because it's 3/4, it's doing this. That's really all you can do, because you're not going to sit there and try to substitute in ordered pairs for this stuff, because it's just awful. You could, but what's the point? See what I'm saying? On a test, I can ask you to rough sketch and give me an ordered pair, because I can still do the same thing if we could tack on an H and a K, and it still does the same stuff, where everything just shifts off from that one ordered pair. Sure. Same idea. Let's make this interesting. Let's say it's y equals 2, oh, we just did 2. We'll say 3 e to the negative 0.5 times the quantity x minus 2 plus 1. Yes, ma'am. Right. Because then it creates a fractional. It's negative, then it's value 2. Then the value is between 0 and 1. That's why that. So here, we're going to follow the exact same rules as we did before. Where we have an H and a K. Now, when you do this, it's like we haven't labeled anything. As you label stuff through, you become less likely to screw something up. So your A value is 3, your R value is negative half, so A, your R is negative 0.5, which means it's decay. Then you have an H value of 2 and a K value of 1. So just like we did yesterday, I'm going to plot the parent graph of this. The parent graph of this would be y equals 3e to the negative 0.5 x. That's going to be my parent graph. When x is equal to 0, what's y? 3. Good. So I only have one ordered pair, 0 and 3. To that ordered pair, what do I have to do to the x and the y value? Scooch it. How much do I scooch it? Over which direction, left or right? Correct. So my scooching would be x plus 2 and y plus 4. Which means this point shifts to become 2 and 4. So my parent graph, since this is decay, so it's doing this. Where do you think your new horizontal asymptote is going to wind up? At 1, good. You still have that horizontal asymptote at your K value, just like we did before. It doesn't change anything. So your new graph then is just that. That's really all you can do about it. That's what's nice about graphing E's. Really only one thing to do. Yes, ma'am. Yes. It's the easiest way to do this. And like I was saying earlier, when people start asking about these things, the more that we get accustomed to plotting and working with the parent functions, the easier, the more complicated stuff when we see it later becomes. Because you'll be like, okay, get a parent function, plot the easy points, and then shift those points. And it's just practice. And I know it's like overkill right now because it is kind of simple. There's a method to the madness in my brain. As difficult as it might be to believe, sometimes I do have a reason for some things. Not all things, just some things. Not terrible? That's really all there is. Okay? That's really all there is to this. This is a pretty, that's why I thought today would be good to just kind of ease back to the graphing, go over anything you had, if you guys had any leftovers on it. I'm going to add the couple of graph notes that are on here. What I have here for you guys, you probably saw on the calendar, are these right here. You've got the 18 through, I'll put it on board so that doesn't see it. So we have, I forgot what page it is on, but it's numbers 18 through 32, every other even. Which means I think you said I end on 30, so do 32, because it's not going to kill you. Then 50 through 60 evens, and then the three graphs are 70, 72, 74. Shouldn't take you very long to pop through. We'll staple these two assignments together from Friday, Monday, or yeah, the 2 days worth of stuff. We'll collect it all tomorrow. Tomorrow what we'll do is we will start then on exponential growth and decay word problems. These are quite literally the easiest things you will see for a word problem in Algebra 2. So there's that. It's like, you have $1,000 in the bank at 6% interest, compounding annually. How much do you have after 10 years? Oh, I look for the formula and I press buttons on my calculator and I hit enter. Okay. What's that? Really? Would the formula work like that? Because it really is, it's just straight formula stuff. If you could, yeah. That's what yeah, because Wednesday we're doing that way you guys you have the top. Oh no, that's okay. It's all right. Yes, sir. Yes, sir. 6.3. What page did that start on? If anybody has it? 483. Thank you. Yeah, make sure you have your calculator charged for tomorrow because you will use them pretty much nonstop. Buttons, buttons, buttons. Did you guys do okay with all the graphics that you just saw from Friday? They're nice. Don't be enthusiastic about it. Show us how to do it. Come on! Chimkey, Air 5, show me how to do it. Better. You guys all just like, it's 2:45. Poor Devin gets to go home soon. Devin, did you do okay? Can't hear you. Hold on. Oh, spell you later, Devin. La da da dee.